Hello, and welcome to the AWS Research IT Training Series. I'm Marcy Collinson, your session correspondent and the Senior Scientific Research Programs Manager for the AWS Research Team. Today, we are delighted to have Varun Pol, Senior Solutions Architect at AWS, here to discuss AWS networking for research IT. Varun has 8 years of experience in cloud computing technology and holds a Master's of Science degree in electrical engineering from New York University. He first joined AWS Cloud Support as a network engineer prior to moving to his current role, helping customers in higher education to accelerate adoption of AWS in their cloud computing journeys. We will reserve the last 5 to 10 minutes of the session for a Q&A portion, but please feel free to place any questions that you may have during the presentation in the questions queue in the GoToWebinar toolbar, and Kevin Maricoshi, Senior Solutions Architect at AWS, will answer them in real time, or we will read them aloud later on. So without further ado, I'll pass the microphone over to Varun. Varun, please take it away.
Thank you, Marcy. Thank you, everybody, for joining us today. Today, in this talk, we'll learn about AWS networking services and its features, and then how these services can support and enable environments and individuals involved in research. In terms of agenda, we'll begin with a quick overview of Amazon VPC and its features, and then go further into discussing various network connectivity options. We'll talk about multi-account scenarios, multi-VPC scenarios, and also a little about hybrid cloud scenarios. After that, we will then take a look at some sample architectures, followed by some data transfer services, which are network-based in AWS, and then end by discussing how we can use certain things within AWS to improve network performance. Like Marcy mentioned, we'll spend a few minutes at the end taking questions from the audience, but if any questions come up in between, feel free to put it in the chat. So going back, I was talking about this slide where I wanted to talk to you about the Amazon's global infrastructure. AWS has the largest global presence in terms of cloud provider with 24 regions across the globe. And we are continuously expanding this global footprint with 5 more announced regions coming soon. The yellow and the orange circles on the slide, each one of these represent an AWS region, which is a physical location where we cluster our data centers. The blue dotted lines that you see connecting these AWS regions, except China region, these represent Amazon's backbone network, which are 100 gig links that are multiple, resilient, and diverse connections. So with our large global footprint and high bandwidth connectivity to our regions, this helps researchers who are looking to collaborate with peers and organizations globally, giving them access to clusters or data around the world. So we spoke about regions, right? These are geographical areas where we cluster our data centers. On the right, we have a logical diagram that represents a region. You will see such representations in our architecture diagrams, in our documentations. The region here is identified as US East 1. This basically says that the region is located in the United States. It's on the East Coast, and it's region number 1 on the East Coast. If you look at the regions, it consists of multiple isolated and physically separate availability zones within that geographic area. An availability zone is a logical group of these data centers, and each availability zone has its own independent power, cooling, physical security, and it's connected via redundant ultra-low latency networks. AWS customers who are focused on high availability can design their applications to run in multiple availability zones to achieve even greater fault tolerance. These availability zones are represented as 2 boxes in the middle, and they're identified as US East 1A, 1B as alphabets. Again, going back to the infrastructure side, within an availability zone, there are data centers, 1 or more data centers, and inside each data center, we have multiple racks, and within these racks, we have hosts running. These hosts are represented as EC2 instances within that AZ. So now we have these hosts running in availability zones. These hosts require routing, they need firewalling, they need connectivity, right? This is where our networking comes into picture with VPC. So a VPC stands for Virtual Private Cloud. It is a logical isolated network section in the cloud. I always tell customers, think of it as your own data center in the cloud where you are running your resources in that data center. Let's look more into a VPC. A VPC exists within a region. It's a regional construct. And within that region, it spans across the AZs in that region. AZ as an availability zone. Right? And you start by defining a VPC by giving it a network range. You can give it a network range with IPv4. It also supports IPv6. Once you've created a VPC, you then add one or more subnets in each of those availability zones. If you look here, I have 4 subnets, 2 in each of the availability zones. We have a concept of public subnet and private subnet. Basically, a public subnet is a subnet that has connectivity to the internet. This is where you would launch your resources that need communication to the internet. Right? A private subnet is a subnet that does not have a route to the internet, so there is no direct communication outside of the VPC. This provides an additional constraint for anyone trying to access your secure resources over the internet. The VPCs have a layer of security called network ACLs or access control lists. These act as firewall, which control traffic inbound and outbound of the subnets. Once you have your subnets defined, you can then place your AWS resources like EC2 instances inside your subnets. Apart from network ACLs, which are applied at the subnets, EC2 instances also come with an additional layer of security called security groups. Security groups are virtual firewalls for your instances to control inbound and outbound traffic for that resource or that instance. Here I want to show the spectrum of the different instance types we have. Amazon EC2 provides a wide selection of instance types and instance sizes, which are optimized to fit different use cases. Instance types comes in various combination of CPU, memory, storage, network capacity, and you get that flexibility to choose the appropriate kind of resources for your applications. Each instance type comes with one or more instance sizes as well, which you can then benchmark and allowing you to scale your resources as per your requirement of your workload. All our current generation instances support enhanced networking, except for the T2 instance type. Basically, enhanced networking provides a higher bandwidth. It provides higher packet per second performance and also consistently lower inter-instance latencies. So if you're looking at applications like high performance computing or machine learning where you need that high network performance, don't forget to enable enhanced networking for that extra network performance boost. Coming back to the VPC diagram, a VPC is a secure boundary and it is logically isolated. You have complete control on what traffic can go in and what traffic can come out of a VPC. In order to enable connectivity to the VPC, AWS offers multiple gateways and endpoints that are connected to your VPC in order to enable that communication. Let us take a look at some of these, which I have on the stack in a little more detail. On this slide, I try to create an example of an HPC cluster diagram. For the purpose of simplicity, I've considered it in a single AZ or availability zone. Basically, what I have here is a VPC with 2 subnets, a public subnet and a private subnet. In the public subnet, I have a master server running, and this is the master server which needs access for me to SSH into it and submit my jobs. and hence I've put it in a public subnet. Then in the private subnet, I have a cluster of compute servers, nodes running, and they communicate with my master server. They don't have any requirement for me to go directly to connect directly to these compute servers. Hence, I place them in my private subnet. Let's say I want to SSH into my master server, and I have to do it over the internet. So I need that internet connectivity to my master server. This is when I use Internet Gateway. Internet Gateway is a gateway that allows internet connectivity to your VPC. Now, I have my compute servers are running in private subnets, and they don't have direct connectivity to the internet. And I need to update my compute servers or download a patch from the internet. And this is when I need my compute servers to talk to the internet, right? So I use a NAT gateway. A NAT gateway is a managed NAT endpoint, which basically masks my EC2 instances running in my private subnet. It masks the IP addresses, translates it, and then talks to the internet. So anybody trying to spoof my traffic outside does not get to know anything about my EC2 instances running in the private subnet. There are times where you want to talk to another VPC from your VPC, and this other VPC can be within your account. It can be in a different AWS account. It can be in the same region, or it can be in a different region. One way to do this is you can go from your VPC all the way via the internet and communicate with the other VPC. But if you want to talk to the other VPC privately, then you can make use of VPC peering. VPC peering is an endpoint which leverages Amazon's backbone network, and hence giving you that private connectivity without having to leave the Amazon's backbone network or go over the internet. There are use cases where you want to have communication with your AWS resources from your data center or your on-premises. This is where AWS supports VPN or direct connect. We'll talk about these in the future slides. No research webinar can be complete without mentioning Amazon S3. Amazon S3s are highly durable, highly available, cost-efficient storage service. A lot of researchers use this to store their data sets, logs, objects, files, videos. And there's frequent connectivity required to download or upload data from your Amazon S3. One way to do this is, again, go over the internet. But if you're looking to connect to your S3 via the VPC, then you can use the Amazon S3 endpoint. This again gives you that private connectivity only to your VPC to talk to the Amazon S3 bucket. Let's look at a multi-VPC scenario, right? Many of our customers use multiple VPCs that are spread across multiple accounts. As you start to scale in AWS, it becomes challenging to manage hundreds of VPNs connections to these VPCs, or hundreds of peering connections to these VPCs. Having a centralized hub that connects to your VPCs becomes essential. This is when AWS Transit Gateway was introduced. Basically, the Transit Gateway is a managed service which connects VPCs and your on-premises network through a central hub. It works on a hub and spoke model. You can route traffic via this Transit Gateway to all your networks that are connected to it. It centralizes your VPN or direct connect connections between your on-prem and multiple VPCs. So now if you have hundreds of VPCs, then you can centralize communication to those VPCs via one VPN connection that's terminating on your Transit Gateway. The Transit Gateway also helps you span thousands of VPCs in terms of scale across different accounts as well. It also supports ECMP. Those who don't know ECMP, in simple terms, it's a routing strategy where it uses multiple tunnels and enables you to scale the VPN throughput. So if you have 10 tunnels, then it logically combines those tunnels as one and then allows you to balance or load balance your traffic across those 10 tunnels, increasing your VPN throughput. The way Transit Gateway connects to your VPCs are through network interfaces. That gives additional flexibility in routing. It also makes it easy for you to connect or disconnect VPCs to your Transit Gateway. And the Transit Gateway consists of routing domains. And this allows you to do complex and advanced routing. And you get to have more granular control over routing your east-west or north-south traffic via the Transit Gateway. Another feature we have seen customers use for multi-VPC scenarios is VPC sharing. With VPC sharing, network engineers get that central visibility and control over the actual network VPC. And researchers, they don't have to worry or have to manage anything related to networking for the VPC. So the way it works is, let's say the network team has a network account and they create a VPC. And when they create the VPC, they enable all the network constructs. For example, they put in the load balancer, they set up the network ACLs, and any routing, and VPC level resources, basically. Since they create the VPC, they get the term as owner. They're called the owners. And once they create this VPC, they create other subnets, and then they can share these subnets to other users, right? So the network engineers then create subnets and share it to researchers. And when the researcher goes into their account and looks for subnets, they can see these subnets in their accounts. Since they're using this shared subnet, they become a participant. And a participant is responsible for creation, management, and deletion of their resources, which they deploy in that subnet. So for example, researcher Y deploys a cluster in the subnet. Researcher Y is responsible for its creation, deletion, management, and also the costs associated with that cluster. And the participants cannot view or modify resources that is run by another participant. So researcher X cannot see what researcher Y is doing or researcher Z is doing in that VPC or that subnet. So now we have a VPC where the network team creates all the network constructs, create the subnet and shares it to the researchers. And now we have researchers who just have to go deploy their resources within those subnets and not having to worry anything about the networking aspect. Now let's talk about different connectivity options that VPC has to offer. We'll start with site-to-site VPN connections. This is used, a VPN connection is used when you would like to connect your on-prem data center to the AWS VPC privately and securely. This is especially used when you want to send traffic that needs to be encrypted when it's being sent. Right? You start with a customer gateway or CGW. This is basically your VPN device or firewall on your end, like a Cisco, Palo Alto, or FortiGate, any vendor that you use. And on the AWS end, the VPN gateway is called VGW, which is a virtual private gateway. And you negotiate and establish a IPsec tunnel between the CGW and the VGW. Each connection comes with two tunnels, primary and secondary. This is for failover and for higher availability. And it supports static routing configuration and also dynamic configuration with BGP. One thing to note here is the bandwidth for each tunnel is 1.25 Gbps. If you have multiple VPCs, then it becomes management overhead to have VPN tunnels connecting to many VPCs. For example, if you have 100 VPCs and all require connectivity back to your on-prem, then having hundreds of VPN tunnels and managing these 100 VPNs is not easy. Instead, you can use a transit gateway, which we discussed previously, as a central hub, and then you can terminate your VPN on the transit gateway. This allows you to have a centralized VPN connection and easy to manage as well. Like the VPN connection before, Transit Gateway also supports static and dynamic VPN configuration with BGP. One thing to note here is there's an extra cost involved with Transit Gateway attachments for data processing. So I put together a diagram showing the different options for VPN connectivity. The first option one is when you have multiple VPCs and you're using a transit gateway. With transit gateway, the advantage is you get to have a centralized VPN. It supports ECMP, so you get to have higher throughput. So for example, if you have 8 tunnels, then it's 8 into 1.25 Gbps, which gives you a total throughput of 10 Gbps. AWS Transit Gateway comes with an additional cost, which is the extra data processing fee involved. The second option is when you have one or few VPCs and you're able to manage those VPN connections. Here, the throughput per tunnel is 1.25 Gbps. The third option is where you get to deploy your own firewall in AWS as a virtual firewall. This can be a virtual Palo Alto instance or a Cisco instance or a FortiGate instance. You get to have control on both sides, on your end with the customer gateway, and then full control on the gateway running as an EC2 instance in VPC. This is used when you have a compliance probably like NIST, where you need to have control over all the devices that's sending traffic. One thing to note here is this is a self-managed EC2 instance. Hence, you are responsible in terms of high availability and failover. As a best practice, we always recommend to at least have 2 instances running, just in case if one fails, then you have another as your secondary. After VPN, the second connectivity option is direct connect. So a direct connect is a dedicated network connection from your on-prem to AWS via a co-location. Usually customers prefer direct connect when you want to bypass your internet connection to avoid any network congestions or network instabilities. In AWS, you have services that are present outside the VPC, like S3, DynamoDB, right? And you have services that are running inside the VPC, like your EC2 instances. In order to get your direct connect established, you start with talking to your APN partner and identify a co-location. A co-location is where Amazon has its router, and then you can have your router, or you could talk to your partner and they could rent out their router. And this is where the connection happens, where you peer directly with Amazon. We call it as cross connect. So basically, it's a fiber connection coming from all the way from your end to AWS. Once you have established this connection, then from your AWS management console, you can choose to talk to your instances that are running in the VPC via a private WIF, or you could talk to your resources that are outside the VPC using a public WIF. In terms of bandwidth, the dedicated connection supports 1 Gbps and 10 Gbps. If you're looking at sub 1 gig, then you can use partners who give you sub 1 gig connections as well. The advantages of direct connect are when use cases like researchers want a dedicated 10 gig pipe to S3 and they don't want to use internet because of the instability, right? Here you have your own fiber connection, which is stable and it's completely dedicated to you. So now they have a public WIF, which is talking directly to S3 bucket. The other advantage with direct connect is it reduces your bandwidth costs. All data transferred over your direct connect is charged at a reduced data transfer rate when compared to the data transfer rate over the internet. This slide is an image which shows the national and regional networks globally. These are networks that many of them peer directly with AWS. These are dedicated networks, especially for researchers in education and academic institutions, which give very high bandwidth and also provide direct connect services to AWS. So if you're a researcher in an education or an academic institution and believe that you could leverage this dedicated directly peered network with high bandwidth, then please reach out to your provider and check with them. In terms of data transfer, there is no cost to upload data into AWS, but there are fees associated with data transfer for data transfer out of AWS to the internet. AWS is committed to making it easier for researchers to use cloud storage, computing, and database services. But there are times where you might have some requirements for you to transfer data out of AWS. For example, let's say you want to download a data that you've analyzed and share it with somebody on your campus. Right? This is where you download your data out of AWS. We want to enable and support this by waiving those data egress fees for qualified researchers and academic customers. So basically, with global data egress waiver, we offer a maximum discount of 15% of the total monthly spending on AWS services. So if you believe that you qualify for the global data egress waiver, please talk to your AWS account manager to get this benefit. Summarizing, we spoke about VPN, direct connect, and also internet connectivity. I tried to compare when you would use which kind of connectivity options. You'd go with VPN if you're looking for private connectivity. It supports IPsec encryption, so all your data transferred is encrypted. This is useful when you have a compliance requirement where you want your data in motion to be encrypted, right? One thing to remember is the bandwidth is 1.25 Gbps if you're not using Gbps if you're not using ECMP. Direct connect gives you that private connectivity. It does not support encryption. If you're looking at encryption, then you will have to establish a VPN tunnel over the direct connect. It supports high bandwidth up to 10 Gbps. We are looking at options to expand that as well. With direct connect, you get global data egress waiver fees, and the data transfer rates are cheaper when compared to data transfer over the internet. Very useful in use cases where you want to have that dedicated, stable connection to Amazon S3 with your public WIF. You can also connect to VPC with internet. This is public connectivity, no encryption by default. If you're using a regional or a national network, then you get high bandwidth, and they peer directly with AWS. And most of them support global data egress waiver as well. Sometimes customers have requirements to share their data or have connectivity with their on-premises or with non-AWS cloud, right? To their AWS cloud. So we spoke about connectivity between your on-premises and AWS. If you're looking at connectivity with other cloud providers with AWS, then you have options where you could use VPN to terminate the VPN connection on a transit gateway or on a VPC in AWS. Or if you're using something like direct connect with the other provider, then you could see if they can connect to the same co-location and also use route distribution to connect with AWS. Moving further, I tried to put together some sample architectures based on the questions we often hear. This slide shows an organization structure. It's a sample architecture with multiple accounts and using organizations for research accounts. This use case is where, especially in universities or educational institutions, where you want to have all your researcher accounts under one organization structure, so that you could have that governance, security, networking, centralized governance, security, and networking, and also enable compliance. For those who don't know what organizations is, it's our account management service that enables you to consolidate multiple AWS accounts into an organization and centrally manage them. So if you look at this architecture, there's a core OU or an organizational unit, which is a group of accounts. So within that core OU, we have a shared services account. This is where you could leverage services that has to be shared, something like your IDP or your authentication services. Then we have a log archive account for logging, storing all your logs. Then we have a security account, and then we have a network account where you could run your network services like Transit Gateway or your firewalls that you want to share with your accounts. Then we have multiple OUs, which I've considered in terms of data sensitivity or compliance. So for example, we have a sensitive OU. This is an OU where you would place all your accounts that are running sensitive workloads. This is where you don't want to have external connectivity to the internet or very limited connectivity, right? Compliance related workloads can be running in this. Encryption is recommended because the data is sensitive, right? Then we have another OU, which is a HIPAA OU. These are accounts where you could put all your research workloads related to HIPAA or any HIPAA workloads, and group them here. So and in terms of connectivity, you can see that I have a network account. It has the green dotted lines, and you can see I don't have it connected to a sandbox account. Trying to avoid that connectivity to the sandbox, because with sandbox, most of the times we have less secure resources there, and if somebody gets into your sandbox, they still don't have a way out to go to your other accounts. This slide is similar to the previous slide, but here we are not having an organizations only for research accounts. This is more in terms where you have multiple AWS accounts and you want to have your research accounts also apart within the same organization as your other accounts, like your department accounts or your IT accounts, right? In that case, you could have a separate research OU so that you can centrally manage them and provide centralized security, centralized networking into that research OU. So in the previous two slides, we spoke about how you can organize your accounts and share your resources centrally. I wanted to quickly highlight how that would look in terms of network architecture. So over here, I have accounts, which are basically VPCs with multiple accounts. And what we can have connectivity across these VPCs using a transit gateway. With transit gateway, you get routing domains, where you can control your east-west traffic. For example, you can control that you don't want your development VPCs to talk to your production VPC, but you can allow your development VPCs to talk to your shared services VPC. So you can control your east-west traffic. You can also have a centralized VPN or direct connect terminating on the transit gateway. And then if you're looking at other networking services or configurations, like probably you want to have an egress VPC for all your internet bound traffic, or you want to have an edge services account where you have your firewall setting, or probably you have a use case where you want to inspect IDS or IPS for your traffic that's flowing between your VPCs or flowing between your on-prem and VPCs, right? So all these network VPCs and network related concept can sit in your network account under that core OU. Our next topic is on data transfer. AWS offers several services to transfer your data and access to your storage in the cloud. Like, depending on how you want to move the data, how soon you want to move the data, or what type of the data it is, or what size of data you want to move, you can choose different options within these, right? Today, I wanted to focus on two of the data transfer services that are more network based. We'll start with Amazon S3 transfer acceleration. So S3 transfer acceleration enables fast, easy, and secure transfer of files over long distances. This is very useful when you have data transfer happening over long distances between your client and an S3 bucket. What happens is it takes advantage of Amazon's CloudFront edge locations, which are globally distributed. If you remember the global infrastructure deck, we have 220 plus edge locations spread across the globe. So S3 transfer acceleration uses these edge locations, and the data is routed to Amazon S3 over an optimized network path. I recommend using transfer acceleration for your S3 bucket for reasons like if you have customers that upload data to a centralized bucket from all over the world, probably there's a research collaboration project going on and there's one central bucket and you have researchers uploading data from various parts of the globe, right? That's when S3 transfer acceleration helps. Or if you're transferring gigabytes to terabytes of data on a regular basis across continents. You can also use S3 transfer acceleration when you feel that you're unable to utilize all your available bandwidth over the internet when uploading to Amazon S3. The other data transfer service I wanted to talk about was Amazon AWS Data Sync. This is an online transfer service. You can use Data Sync to migrate active data sets to AWS, or if you want to archive your data to free up your on-premises storage capacity, or even transfer data to the cloud for analysis or processing. The data sync is built in a way where it uses a purpose-built network protocol, and it leverages parallel multi-threading architecture to accelerate your data transfer. This speeds up the migrations or any recurring data processing workloads for analytics and machine learning. The features, in terms of features, it's very easy to use. You don't have to write any scripts or code. It's simple to manage. You can manage it via AWS Management Console, or you could use the Amazon AWS command line interface or SDKs. It supports Amazon CloudWatch, so you could monitor via Amazon CloudWatch. In terms of security, data is validated, and it supports encryption in transit and at rest. It also supports automatic recovery from I/O or transmission errors if anything happens when data is being transmitted. It also supports PCI and DSS compliance. It is HIPAA eligible. It supports IAM, so identity and access management control is available, and it's integrated with AWS CloudTrail, giving you that option to log any API activities. In terms of cost, like any other AWS service, it's usage-based, so you only pay for what you use. So with transfer acceleration and AWS Data Sync, you get that high-performant services for you to transfer your data into Amazon very quickly. Okay, we are on the last topic on improving network performance. So if you have workloads that require high throughput, especially between nodes, inter instances, then it is recommended to use placement groups. Placement groups provide high network throughput between the instances. They're very useful for tightly coupled node-to-node communication that is typical of HPC or HTC applications. Basically, the placement group is a logical grouping of instances within a single availability zone. What happens behind the scenes is all your instances are grouped and placed in the same high bisection bandwidth segment of the network, and this allows it to enjoy a very high per flow throughput limit of TCP/IP traffic, which is why they get that high throughput and low latency because of its placing of each other in the same bisection. One thing to note is placement groups work in the same availability zone. So all your nodes have to be in that availability zone. We realize that researchers need high performance. They want reliability, low latency, and a jitter-free network. Right? With Elastic Fabric Adapter, it's a network device that you can attach to your Amazon EC2 instance to accelerate HPC and machine learning applications. EFA provides very low latency. It provides high throughput when compared to TCP transport, which is traditionally used in cloud-based HPC systems. Well, it enhances the performance of inter-instance communication that is critical for scaling HPC and machine learning applications. It has a congestion control. For those who know TCP, EFA uses a congestion control protocol that is better than TCP. What it does is, on a high level, whenever your application has to talk to your network interface, it goes via the OS. So the OS gets involved in those messages. What EFA does is it uses something called a technique called OS bypass, which basically is whenever an application talks to your network interface, it doesn't get the OS involved. So this reduces the overhead and allows the application to run more efficiently, and also gives you that higher throughput. So if you're using HPC or machine learning applications and requiring high throughput, enable EFA on your EC2 instances. Okay, we are almost at the end, and I tried to save the best for the last. AWS recently released Amazon EC2 P4D instances. This instance delivers the highest performance for machine learning training and high performance computing applications in the cloud. These instances are the first in the cloud to support 400 Gbps instance networking. Along with networking, these instances also provide very high compute performance and storage. So for researchers and data scientists uh, who want to train ML models, especially the most complex multi-node ML training for use cases like natural language processing or building recommendation engines or object detection and classification, or HPC applications like seismic analysis or genomics or financial modeling and more. This is the instance they can consider taking a look at. Wrapping up, if you're looking at for more deep dive training on AWS networking or any other topics, we have a ton of resources in our documentation, videos, and also on our AWS training website. If you're further interested in our certifications, please explore our certifications for network specialty as well. With that, I want to thank you for attending this webinar and open it up for any questions.
Fantastic. Thank you so much, Varun. What a wonderful presentation. We did have a couple of questions come in through the queue about this session being recorded, as well as what will the presentation deck be available. And a link to the recording and the slides will be emailed to you in a few days if you registered for this session. So you will be getting that information. So watch for that in your inbox. And I'm going to just jump to some questions. Question number 1, can we get 10 gigabyte encryption BW with AWS?
So I think BW bandwidth, right?
Bandwidth, yeah.
Yeah. So encryption, like I said, right? VPN supports encryption by default. If you're looking at direct connect, it doesn't support encryption as of now. So if you're looking at if your requirement is 10 gigs of encrypted bandwidth, then I would recommend using Transit Gateway with ECMP. With ECMP, you could then have multiple tunnels, like 8 tunnels, which gives you 10 gigs of bandwidth, and then with that you get that encryption.
Great. Next question, when should we use direct connect versus internet?
Yeah, I tried to cover this in my discussion. So direct connect gives you the dedicated connection, and it also is stable, and it's your own pipe. So when you're using internet, internet is shared, so and it's not stable as compared to a direct connect. So if you're looking at a more dedicated connection with a dedicated bandwidth and stability, like use cases where you want 10 gigs of non-interrupted, highly stable connection to your S3 bucket, that's when I would recommend using direct connect. Also, if you're doing a lot of data transfer, direct connect data transfer rates are cheaper when compared to your internet data transfer rate.
Wonderful. Next question, to get me started, is there someone that can help us review what I need and point me at the right direction?
Definitely. I would start by recommending to talk to your AWS account manager. They are your point of contact, and they can get you connected to other resources within AWS. And like I also mentioned, there are many other resources in terms of our documentation videos, which you can leverage. I also have our contacts put at the end, so please reach out if you have any questions or if you need any help.
Yeah, thanks. And then in the group chat, I went ahead and put some information in there, including our seminar series Alias, which is AWS AWS-WWPS-seminar@amazon.com. If you email that alias with any questions, or if you don't know who your account manager is, we'll be happy to make sure that you're put in touch with the correct person. All right, next question is, can we use our own traffic engineering with any of these AWS solutions? If yes, which is the best option?
If you're using a specific vendor on your on-premise for traffic engineering or any specific protocol, then you take a look at our AWS Marketplace for any options. This is where you want to do traffic engineering between your on-prem and your VPC. If you're looking at traffic engineering on your end in terms of BGP, then yes, you could advertise your network and you could do traffic engineering from your end. But if you're looking at specific devices or specific vendors that you want to leverage within AWS, then take a look at AWS Marketplace, and you can search for your vendor specific, and you can launch them within AWS.
Great. Next question is, will you issue an attendance certificate? We do not typically issue attendance certificates, but that's not a bad idea. So thank you for bringing that up, and we'll contemplate whether or not that's something we should adopt. Next question is, any IoT related resources available in RENs?
So I guess I'll take this one. I'm Kevin. So AWS has a whole IoT service chain that works through the normal networking. If you're communicating to AWS via the REN, then you can use that pipe to get to your IoT resources. This will depend largely on where the IoT devices are sitting. If they're sitting on the cell phone modems, then you're going to be going over the public internet and you wouldn't use the REN. But if they're attached to, say, a university network, Wi-Fi network, a university radio extended network, then those would travel over the REN to get to AWS. I hope that kind of got where your question was going.
That was a great answer. Thanks, Kevin. Next question is, does AWS support jumbo frames?
So AWS does support jumbo frames, but go ahead, Varun.
No, okay, you can complete and I can add.
Okay, it supports jumbo frames. Yeah, go ahead, Varun. It's easier.
Okay, I can take that. So yes, we do support jumbo frames within the VPC to VPC, or if you're looking at jumbo frames from a direct connect to VPC. Transit Gateway also supports jumbo frames. I think Transit Gateway supports jumbo frames up to 8,500 MTU and not 9,500, but it does support jumbo frames. VPN does not support jumbo frames. So if you're looking to transfer data from your on-prem to AWS via VPN, then jumbo frames packets will be dropped. It doesn't support. And also, if you're trying to transfer via internet, packets may be dropped.
Great. What is the bandwidth for EC2 instances?
Kevin, do you want to take it? Or I can?
Yeah, I'll take that one. Yeah, so EC2 instances all come with have varying quantities of bandwidth, and you'll have to look at the instance descriptions to determine what bandwidth they support. In general, as we said, they'll support up to 400 gigabits with the EFA on a P4DN instance, and they go down to to shared capacity on 1 gig links. It's important when you're thinking about your application, you keep in mind what the network throughput requirements are and match EC2 instance type to that. If you're working with very small instances, they will have less bandwidth, and you will need to be a little bit cognizant of what you're doing with them.
Wonderful. Well, I think that's all the questions that we have. So I want to thank Varun and Kevin again. And I would like to encourage our audience to attend, to please join us for AWS reInvent 2020 from November 30th to December 18th. This year's virtual 3-week conference is free to join, and will offer 5 keynotes, 18 leadership sessions, and unlimited access to hundreds of sessions on core services and emerging technologies, all at no cost. I went ahead and put a link in the chat to the reInvent homepage, so please go there to find more information. And before you leave, please take a minute to give us feedback on today's session. A short survey will pop up on the screen as we close out. We host these webinars for the research community, so any feedback you have is valuable, and we will help will help us to continue to deliver content that the community cares about. I also wanted to let you know that in the chat, I went ahead and put a link to our AWS Education Research Seminar Series homepage, which has session recordings and information about upcoming presentations. And if you have any questions about past sessions or ideas for future presentations, please email us at aws-wwps-seminar@amazon.com. And you can also email us there if you have any specific questions pertaining to your institution. We want to thank you all today for attending. We hope you enjoyed the presentation as much as we enjoyed putting it together for you, and we wish you all a wonderful holiday season. Thank you.